Okay, now let's start with the first application um, of the momentum's equation, that is the fluid jets. The following assumptions are made about a fluid jet. First of all, what is a fluid jet? It's just a jet of fluid. There are various applications where a jet of fluid is being used. The the following assumptions are made about a fluid jet. The pressure is constant and equal to ambient pressure across any cross-section of the jet. Okay, so suppose this is a fluid jet, and then at any cross-section, the pressure is equal to atmospheric pressure. So that means the force due to the pressure of the jet is not going to be applicable within the jet itself. Okay. Thus, when a free jet crosses a control surface, it does not exert a force. Because for force, we need to have pressure, but if it is just the atmospheric pressure, that's considered zero gauge all the time, right? So this is the first assumption that we make for jets. Then the fluid velocity is uniform across the jet cross-section of the jet, across the cross-section of the jet. So if I have a jet at any cross-section, over the entire cross-section, it's the same velocity. So we are not saying that at the edges, the velocity is higher or lower, and then as we move towards the center of the jet, the velocity is changing. Okay. So what we are saying is that from top to the bottom, the entire jet has the same velocity. So there is no change in the velocity. This is an assumption. Obviously, in reality, it will not be the same. But this is an assumption that we make in order to simplify our problems for solution. The third assumption is that the fluid jet has a momentum which is used in momentum equation. Okay, yeah, this is a general thing. So let's start solving some problems related to it. The sketch below shows a 40-gram rocket of the type used for model rocketry. Okay, so a small model of rocket is made. That's 40 gram. Being fired on a test stand in order to evaluate thrust. Okay. You can see here, this is the rocket. Okay, this is a small rocket, 40 gram. Okay, and we put the fuel inside the rocket because this is a model, so it should be accurate. Okay, so fuel is put inside the rocket, and then obviously the fuel is producing the thrust so that the rocket can go up. But since we want to measure the thrust, so we connect the rocket with this supporting beam. So we have a supporting beam here, and with this support, it is being connected. So the rocket cannot move up, but this supporting beam can calculate the thrust which the rocket is actually, which the gases are making to push the rocket up. Okay, and that's the objective of this experiment, to calculate how much will be the thrust in this model and then estimate it for the case of the actual case. Okay, so anyways, this is a situation that we have 40-gram rocket used for model rocketry being fired on a test stand. This is a test stand, means laboratory setup, in order to evaluate thrust. The exhaust jet from the rocket motor has a diameter of 1 centimeter. Now this jet which is coming out, exhaust jet coming out from the rocket, has a diameter of 1 centimeter, a speed of 450 meter per second, and a density of 0.5 kg per meter cube. Assume the pressure in the exhaust jet equals ambient pressure. Inside the pressure is equal ambient pressure. Okay. And neglect any momentum changes inside the rocket motor. Find the force FB acting on the beam that supports the rocket. Okay. What will be the force that will be acting on FB, where on this beam? This force, which will be acting on the beam, we need to find that. Obviously, that force depends upon how much is the thrust by the rocket. Okay. So force depends upon how much is the thrust by the rocket. Okay. So first of all, this is the problem statement. Before moving towards the solution, the first thing is that we need to know that do you understand the problem statement and the figure? So we have a small rocket placed in a laboratory setup, the 40-gram rocket, okay, and it's placed on a test stand, and then the rocket is fired. So the gases are coming out of the rocket, which is producing the thrust, but we don't want the rocket to move up because it's a laboratory setup, so we attach it with a support beam. So the beam is holding the rocket in its place, but we can now actually calculate that how much is the thrust produced by the rocket by finding out how much is the force supported by the beam to hold the rocket in place. Okay, then we can find out, it is determined that what is the velocity of the jet. We can find out, it's measured that what is the diameter of the jet, this exhaust jet. Okay. And then what is the density of the jet? Okay. So these things are measured, and now what we want to find out, we need to find out that how much is the force of beam. Do you understand the problem statement and the figure associated with the problem? Is there anything which is not clear to anybody? If it's clear, then we are going to move towards the solution. Okay. So let's move towards the solution. The first thing is that what we are going to do is we are going to draw the force diagram and the momentum diagram. Okay. So in case of the force diagram, we are going to draw our control volume. So our control volume is the rocket. Okay. And we are going to show what are the forces here. So first thing is the force of the weight of the rocket, which is 40 gram. Okay, so weight will be acting downward, shown here. Then we will have the force on the beam, and the force of the beam will also be in the downward direction, like because the rocket will be trying to move up, so the beam has to apply force to hold it down. Okay, so that will be in the downward direction. So these are the two forces. That's it. You don't have any other force here. Then let's look at the momentum diagram. In case of the momentum diagram, we are going to focus we're going to focus over our control surface. So this box, dotted box, is our control surface, and we are going to look that what fluids are going in and out of this surface. So one thing is clear, that there is no fluid going into the surface. Yes, but there is a fluid jet which is actually going out. So we have only one outlet, but we don't have any inlet. Okay, so that's that outlet we are going to mention. We are going to show with an arrow downward and m dot v to show that, okay, this is the flow going out and the momentum is m dot v. So that's the momentum diagram. So we have drawn the free body diagram and momentum diagram. Suppose this is a 10 marks question. So 1 mark for free body diagram, 1 mark for momentum diagram. Okay. So you solve the problem perfectly with no errors in it, but did not draw the diagram, so you lose 2 marks out of 10. Okay. Okay, now here in this case, if you look here, we have the forces in the y direction. There is no force in x direction. There is no force in z direction. All the forces in the y direction. And we have also the momentum in the y direction. there is no momentum entering or leaving in the x direction or z direction. So that means since the forces are all in the y direction and momentum is also in the y direction, we just need the y component of the momentum equation. We don't need any other equation. Okay, so we are just going to use the y component of the momentum equation. Here actually they've used a z component, but in reality it should be y component. Okay, okay, either we call this as y component, or in the diagram here, instead of writing this as positive y, should write here as positive z. Okay. So if we write here positive z, so that means we just need z component of the equation. So this is our z component of the equation. Summation of the forces in the z direction equals to the momentum accumulation term plus summation of all the momentum going into the control volume minus summation of all the momentum of the fluid going out of the control volume. Sorry, plus the momentum of all the fluids going out of the control volume minus momentum of all the fluids going into the control volume. Inlet will always be considered as negative. Okay. So first of all, we don't have any accumulation term. This will be 0 because our rocket is a fixed size and the dimensions of the rocket are not changing. So our control volume dimensions are not changing. And the mass and the density of the fluid inside the rocket are also not changing. Okay, so flow is steady. Whatever the fluid is coming out of the rocket, the exhaust of the rocket is, we are assuming it to be steady. So that means momentum accumulation term will not be there. Okay. So now we are left up with these three terms. Let's talk about any flow inlet. So there is exhaust coming out, but there is nothing going in. So inlet term will also be 0. So what are we left up with? We have the exhaust, which is the outlet. So we'll have one exhaust, and obviously then the forces that we have to consider. Okay. So let's consider the forces. So forces in the z direction. Given that if we say that our z direction is positive upward, so FB and weight both are in the negative z direction. Okay. Since both are in the negative z direction, so we can write summation Fz will be negative Fb, negative W, or W can be written as mg. So we'll get this as one equation. That will be the summation of forces. Okay. So this will be this term, summation Fz. Okay. Now let's discuss about this term. The momentum going out of the control volume. Inlet is 0, that is clear. Okay. For outlet, there is some concept that you need to understand. It's written summation m dot o m dot outlet v outlet in the z direction, right? First of all, summation sign will go because we have only one. We don't have more than one outlet. We have just one outlet. Okay. So summation sign will go. The next thing is that we have here m dot. Okay, velocity in the z direction. It will be in the negative z direction. Velocity will be in the negative z direction. So you look here in this diagram, it will become very clear. Look here, our z direction is upward positive, and the exhaust is going in the downward direction. So velocity is in the negative z direction. Okay. So if the velocity is in the negative z direction, okay. So what I was telling us that M dot is the mass flow rate, okay, and then we have V not V outlet in the Z direction. Okay, since the Z direction is positive upward and V outlet is actually going in the downward direction, so I will write here negative V. Okay, so that will be the negative V here. This negative V is for here, right? Now, we know that something that we studied in the last class, when we were discussing the rate of flow. So mass flow rate, the formula for the mass flow rate is m dot is equals to rho a velocity. Okay. Now here, when I'm actually calculating the mass flow rate, I just need the magnitude of velocity, irrespective of what is the direction of velocity. Okay. So if I write here, then I will write here like this, rho a v multiplied by negative v. So it will become negative rho a v square. The point of understanding is that this velocity here is the directional component. So we have to consider the direction. Is it positive or is it negative? But when we are going to use the velocity here, in order to calculate the mass flow rate, we just need the magnitude, irrespective the velocity is positive or negative. Now, what the mistake a student could do, that student might think that, okay, the velocity is in the downward direction, it's negative. Okay, so they will put a negative v here, as well as they put a negative v here. What will happen? The result would be, instead of getting negative rho av square, they're going to get positive rho av square, which will be wrong. Why? Because in this formula, the velocity which is associated with the momentum, for that we have to consider whether the momentum is positive or negative. But in order to calculate the mass flow rate, we don't need to check whether the velocity is positive or negative. We just need to know how much the mass flow rate. Mass flow rate itself is a scalar quantity. Mass flow rate is not a vector quantity. So I just need the magnitude of the velocity here. Don't need the direction. This is the basic concept that students get confused, that either they don't use the negative sign at all in both the velocities, or they use in both the velocities, and this is wrong. Okay, because the velocity which is used here in calculating momentum, for this direction needs to be considered, because momentum is also a vector quantity. So we need to know whether it is positive or negative. But mass flow rate is a scalar quantity. Okay, so when we are using the velocity to calculate the mass flow rate, that velocity would be the magnitude only, irrespective of what was the direction of the velocity corresponding to our references mentioned. Is it clear? So here we will have negative rho a v square. Is this thing clear? If there is any point which is not clear, let me know. Okay, so now we have the outflow component, we have the inflow component, we have the accumulation term 0, we have summation fz. Just substitute everything. If we substitute everything into the main equation, our main equation becomes like this. Or since we want to find out fb, okay, so fb is equals to rho a v square negative mg. Just substitute the values of, we know density, we know area. Area would be what? Pi by 4 d square. Okay, since the diameter is given, so area will be pi by 4 d square multiplied by the velocity square minus m into g. So we're going to get how much is the force. So 7.56 Newton is the force needed to hold this rocket together. That means this is the thrust which is being applied by the exhaust gases over the rocket. Okay. So this is the solution of the problem. Is there anything within this solution which is not clear to anybody? Please feel free to ask. Is it clear? Okay. Okay, now let's see this another problem. Concrete flowing into the cart. As shown in the sketch, concrete flows into the cart sitting on the scale. The stream of concrete has a density of 150 pound mass per feet cube, an area of 1 feet square, and speed of 10 feet per second. At an instant shown, the weight of the cart plus concrete is 800 pound force. Determine the tension in the cable and the weight recorded by the scale. Assume steady flow. Okay, so here this is the situation. We have a cart here. Okay, this is the cart. Okay. And concrete is coming from the top in the form of a jet. Okay, and is then filling the cart. Okay, because the concrete is not coming vertically, it is coming at a certain angle. So we need a support beam to hold the cart in place, because if we do not have this beam, what will happen? When the concrete will enter into the cart, there will be a force applied on the cart and the cart will move in this direction. Okay, so in order to hold the cart in the same location, in the same place, we need to have a support beam to hold the cart in place. Okay, and this cart is there on the scale. Okay, the concrete is coming at an angle of 60 degrees from the horizontal. Okay. So this is the situation for the case of the concrete. We know what is the cross-sectional area. We know what is the density of the concrete. We know what is the velocity with which the concrete is coming. Okay, the scale is giving some reading as well. Okay, we need to determine the tension in the cable and the weight recorded by the scale. The thing is that it's mentioned that at this instant, the weight of the cart plus concrete is 800 pound force. So at this instant, whatever the amount of concrete it has, actually the weight of the cart is with the concrete is 800 pound force. But in reality, what do you think? The scale is going to give more weight or less weight? So you have some container and you're throwing water or any fluid into the container. Because of the force of the water, the scale is going to give a bigger reading than actual how much it is. Until and unless you stop the flow of the fluid, you're not going to get the right reading. Because the container is going to be, or the scale is going to be the reading that how much the force it is supporting. Now the force is not just the force of the weight, it's also the force of the jet, which is mixing with the force of the weight. So the scale is going to give a bigger reading. And this happens all the time. Like for example, if I have a weighing scale here and I stand on it, I have to first stand on it and then stop a while until it becomes stationary. Because I have suddenly entered onto the scale, so there is the force of momentum, of my momentum, which is added to my weight. And so the scale is directly going to jump high. And then after I have become stationary, it will become stable at some point. And when it is stationary, then I measure that what is my weight. Actually, digital response is comparatively slower than analog. So digital में ये चीज होती नहीं है. ये जो transactional jerk आता है हमारे पास, वो हाँ अगर digital बहुत ज़्यादा sensitive हो, तो फिर उसमें transactional jerk भी feel होगा, ठीक है. अदरवाइज एनालॉग के अंदर तो ये चीज होती है. आप जैसे ही आप एक स्केल के ऊपर स्टैंड अप करते हैं या उसके ऊपर कोई भी वेट डालते हैं, इनिशियली वो थोड़ा सा फ्लक्चुएट करता है. वो फ्लक्चुएशन क्यों होती है? क्योंकि इनिशियली इट्स नॉट जस्ट टेकिंग द वेट, बट इट इज आल्सो एडिंग द मोमेंटम इज एडेड टू इट. लेकिन जब वो चीज स्टेशनरी हो जाती है तो मोमेंटम का इफेक्ट खत्म हो जाता है, फिर सिर्फ वेट बाकी रहता है. So then you can actually measure that how much is the weight of that thing which you are trying to figure out. Okay, so this is what is happening here as well. Now there is concrete which is now falling on which is now filling this cart. Okay, तो ये स्केल पे रखा हुआ है, लेकिन स्केल अभी करेक्ट रीडिंग नहीं देगा. स्केल रीडिंग ज्यादा देगा. क्यों? क्योंकि कंक्रीट अभी फॉल हो रहा है, तो मोमेंटम ऑफ द कंक्रीट इज एडिंग टू द वेट. Okay, but हमें ये पता है कि इस वक्त actually इसका weight है कितना with the concrete, but we need to find out कि actually scale क्या reading देगा हमें, ठीक है ना? उसके लिए हमें अब momentum of that concrete वो add करना पड़ेगा weight के साथ, ठीक है? वो फिर हम that is possible if we solve the momentum equation for the fluid flow, because concrete is a fluid which is flowing inside the cart right now in the cart. Is this thing clear? Before moving towards the problem solution, first thing is that the problem statement should be very clear to you. Okay, so you have a cart, concrete is falling at a certain angle, तो एक cable भी attach की हुई है ताकि cart अपनी जगह से move ना हो. So that's about that cable will also have tension in it. So we have to find out how much is the tension in the cable. Then we know that at this instant, what is the weight of the cart plus concrete, but we know that the scale is going to give a higher reading. How much will be that higher reading that the scale is going to give? This is something new. So we need to find two things: the tension in the cord to hold the cart in place, and what will be the reading given by the scale now, if we know what is the actual weight. Okay. So this is for the case of the concrete which is falling into the cart, we know what is the density of the concrete, we know what is the cross-sectional area of this jet. There is a jet of concrete which is falling, okay, and we know what is the velocity of this concrete. Okay. So this is the problem statement. If anybody have any question regarding the problem statement, you can ask. Okay, so once we have understood the problem statement and the figure, so now let's move towards the problem solution. Okay, if we look in this problem, we have the concrete which is actually falling at a certain angle. Since the concrete is falling at a certain angle, so you will have the velocity component in two directions. You will have the velocity component in the vertical direction, and you will have velocity component in the horizontal direction. So it will be a two-dimensional problem. Okay, previously with the rocket case, it was one-dimensional problem because all the components were only there in the z direction. But here you will have in z direction as well as in x direction. Okay, so you'll have two components here. So obviously two equations of momentum will be used. So now the first thing, as I told you, that the first thing would be to draw the free body diagram. So for the free body diagram, we have two diagrams. One is the force diagram, other is the momentum diagram. So in the force diagram, we just show our control volume and then what are the forces acting on the control volume. So here we have our control volume here. And what are the forces acting? We'll have the weight of the cart plus concrete, which will be acting downward. This is one force. Then obviously, since this cart is standing on the scale, so there will be the normal force of the scale acting in the upward direction. So that will be the normal force. And then this cart is held with a cord. Okay, so there will be tension in the cord. When the concrete is falling, it will try to move the cart because the concrete is coming at an angle. So it will try to move the cart, but the cart is held by a cord. So there will be tension in the cord. Okay, so these are the forces. Other than these three forces, we will not have any other force. Okay, then this is the force diagram. Then the next thing is we need to draw the momentum diagram. In case of the momentum diagram, we just have to show the flow into or out of the control volume along with the momentum. Okay, so here we have just one flow which is going into the control volume and there is nothing going out of the control volume. Okay, so we have m dot v which is coming at an angle 60 degree into the control volume. So now we have developed the momentum diagram and force diagram. Development of momentum and force diagram, is it clear to everybody? Is there anything which is not clear to anybody? Okay, now one thing is clear that we have to draw, we have to solve two equations here, one in the x direction, other in the z direction. Okay, so let's first see the x direction. Okay, in the x direction, we will have force component, obviously, this tension will be in the x direction. Okay, And in the x direction, okay, accumulation term, momentum accumulation term will not be zero, will not be there. It will be zero. Okay. So because the dimensions of the card are not changing, our control volume is not changing, and we have the steady flow. It was mentioned in the question that the flow is steady. Okay, so obviously because of these reasons, we will have a momentum accumulation zero. Okay, do we have any fluid going out of the control volume? No, we have just fluid coming into the control volume. So there is no going out in the x direction. So this will be also be zero. But we will have a component of the fluid coming in the control volume in the x direction. Okay, so this term will not be zero. So now similarly, again, look here, summation fz. So we have forces in the z direction. Accumulation term will again be zero for the same reasons. There won't be any fluid going out, but we will have component of fluid coming in. Okay. So now we simplify it. Let's talk about the forces. Forces in the summation of forces in x direction. There is only one force, which is the tension. Okay, and our x direction is considered positive like this, so it should be negative t. Okay, so we have summation fx as negative t. Then in case of the z direction, we have summation fz as n minus t. N is the normal reaction in the upward direction, weight in the downward direction. Okay, so these are the summation of forces. Now momentum accumulation terms, or momentum accumulation will be zero in any case. So these are already mentioned here. These are zero. Okay. Now let's talk about momentum inflow and momentum outflow. Okay. Momentum outflow is zero in any case, that we have already cancelled. Momentum outflow is zero. Let's talk about momentum inflow. In case of momentum inflow, we'll have the formula here as, first of all, we have only single inflow. We don't have more than one inflows. So I can remove the summation sign. Okay, so we have m dot I v I x, m dot I v I z. Okay, so once again, when we are using m dot, for this we just need the magnitude of velocity. We does not care what is the direction of velocity here. Similarly, when we are using m dot I here, we just need the magnitude of velocity. We don't care what is the direction of the velocity here. Okay, so that m dot I will be rho a v and all I, rho I, ai, vi. Okay, but here rho I, ai, it's okay. That's the density and the cross-section area, but the velocity, just the magnitude, irrespective of what's the direction. Okay. However, when we are using here vix and viz, now the direction is important. So we are going to consider the direction. Okay. So now look, let's have a look at our problem here. So velocity will have an x component, in this case in the positive x direction, and the z component in the negative z direction. Right? So z component velocity will be in the negative z direction, x component velocity will be in the positive x direction. Okay, because the flow is coming like this. So if you look here, for the x component is just mv cos 60, and that is equals to rho av square cos 60, and for z direction it's m negative v sine 60. Why negative sign? Because z component of this velocity will be in the negative z direction. Okay, so negative v sine 60, and then m dot here will be equals to rho av, so it becomes negative rho av square sine 60. So this becomes this term and this term. Are these terms clear or not? Okay. So momentum outflow is also clear. Now once you have all these things clear, now what we can do is that we can write down the equations in the x direction. It will become negative t equals to negative rho a v square cos 60. Just substitute the values, you can find out how much is the tension. In the on the z axis, it becomes n minus w equals to negative rho a v square sine 60. So since we know what is the weight of this cart with the concrete, and we know density, area, and velocity, so we can find out that how much is the normal force. So normal force will be 1200 pound force. So actual weight was 800 pound force, but then about 403 pound force was added because of the momentum of the concrete. So if the concrete flow was stopped, then the scale would have given the reading 800 pound force. But because the concrete was flowing, the momentum of the concrete was adding to the weight. And so the scale was giving the reading of 1200 pound force. Okay. So fluid force was actually being added in the with the weight to give the reading on the scale. So that's the solution of this problem. Is the solution clear? Is there anything within the solution which is not clear? Any step, any concept, any sign, any term, any value, submission, addition, substitution that you do not understand, please feel free to ask. Okay, let's see another problem. It's very similar to the previous problem, so I'm going to go a little bit faster on this problem case. Okay, we have a water jet of diameter 5 centimeter and speed 18 meter per second. Is filling a tank. The tank has a mass of 12 kg and contains 20 liters of water at the instant shown. The water temperature is 21 degrees centigrade. Find the minimum coefficient of friction such that the force acting on the stop block is 0. So the thing is that here we have this water container, and there's water entering into this container in the form of a jet. Since it is coming at a certain angle, so it is going to push the container in the direction of the flow. Okay. So, but what we do is that so that the container don't move from its place, we put a block. Let's call it a stop block. We put a block here at this point. So this block, the friction of the block with the surface is going to hold the container in place. We're not going to allow this container to move. Now we want to know that what should be the minimum coefficient of friction so that the container does not move. Okay, so we want to know what should be the minimum coefficient of friction between this stop block and the surface, so that whatever the jet of water is coming, that does not move the container, and that is not able to move the block from its place. Okay. So this is the question, very similar to the previous question. Okay, so first what we are going to do, we are going to draw the free body diagram, that is the force diagram and the momentum diagram. We have three forces here: weight, normal force, and then we have the force of friction. Remember, the force of friction always acts in the opposite direction to where the force is applied. So in this case, because of the momentum of the jet, the container will be trying to move here. So the force of friction will be applied in the opposite direction. Okay. And the force of friction depends upon the normal reaction. So it's basically mu n. Okay. And then we have just a single momentum of the fluid flowing into the control volume. Okay, so we solve this problem for x and y coordinate. Let's say x coordinate in the x direction, y coordinate is in the vertical direction. So we write down the y momentum equation. Accumulation term is 0. No need to mention that. We already discussed it. Okay, there is no there is no fluid going out of the control volume. This term will be 0. Summation Fy will be n minus w equals to this term. Okay, so we'll have an equation for n. Then summation of force. Then we can write the equation for the x momentum. So summation of forces in the x direction will be equals to all the momentum of the fluid going out of the control volume, the x component of those momentum minus the ones going into the control volume. There is nothing going out of the control volume, so this term will again be 0. The x component will only have this friction force, which will be equal to mu n, and it will be in the positive direction. Okay, and then we'll have the y component, x component of the momentum going into the control volume. Substitute the values, you're going to get an equation for mu. Then we already have equation for n previously. You just substitute it into the main equation, substitute all the values. You're going to get what is the minimum. You're going to get what is the minimum coefficient of friction needed to solve the problem. Okay, is the solution clear? Is there anything within the solution which is not clear to anybody? Okay, so if the fluid jets is done, next is the topic of nozzles. Shall we start the topic of nozzles, or shall we give you a break for the quiz? Okay, so let's stop our lecture here. We'll wait about 10 minutes, 10 to 15 minutes. We're going to start our quiz. Okay.